Hey there! In this last unit of Chapter 5, we're going to be taking a look at rock units and how they're related to each other. One of the things that we need to look at is this thing called a lithostratigraphic unit. Remember that litho means rock and strata means layers. So we're looking at rock layered units. So a rock layered unit, a lithostratigraphic unit, is just a body of sedimentary, extrusive igneous, metasedimentary, or metavolcanic rock that's deposited on the surface of the earth, and they're distinguished, these layers are distinguished from one another on the basis of lithologic characteristics like their texture, their color, the composition of the rocks, and they're also distinguished by their stratigraphic position. And the smallest lithostratigraphic unit is called the bed. Since you first started in geology, you've probably heard this word formation. And formations of rocks are mappable units. They're thick enough sedimentary units that are mappable from one place to another. So if you just have a thin layer of rock that peters out locally, like within a few hundred feet even, that's not a formation. So formations have to be distinct and different from rocks above and below. They're usually composed of either a single rock type or a characteristic set of rock types. As I said, they're traceable from place to place, from exposure to exposure, and they have sufficient thickness to be mappable. And they're named after a geographic locality where it is well exposed. Here are some other words that you'll hear in lithostratigraphic units when people are talking about it. So formations can be divided up into members, but you can have formations, and a group of formations is called a group, and then a group of groups is called a supergroup. Lithostratigraphic units can cut across timelines. So you can have a unit or formation that straddles the Silurian and the Devonian. So this is called diachronous. Another term you'll need to get to know is this word facies. Now, facies are the characteristics of a particular rock unit which can be used to interpret the depositional environment. And we've been looking at rock units and how you interpret them. And so these are we've been looking at facies. Now, each depositional environment grades laterally into other depositional environments. Depositional environments aren't just this one solitary unit that doesn't touch anything else. Think about it. If you're in a transitional environment, the transitional environment touches rocks that are in a marine environment, and it also touches rocks that are on the land. Over time in the rock record, we see sea level changes, and these changes are recorded in the rock record as transgressions and regressions. A sea level rise is called a transgression, and a transgression produces a fining upward sequence of facies. Think about it. As the water rises, we're going to get the deeper water facies depositing on top of the shallower water facies. So we'll have a siltstone deposited on top of a sandstone, or a clay stone deposited on top of a siltstone, deposited on top of a sandstone, deposited on top of gravel. So that is an example of transgression, a sea level rise. These are sometimes called ONLAP sequences. So if you read that word ONLAP, it's the same thing as transgression, sea level rise. In this picture, we see sedimentation during a transgression, which produces this ONLAP sequence. Notice that in each successive picture, the sea level is rising. And as the sea level rises, the sediments that used to be deposited farther out are now being deposited inland. In the bottom drawing, you can see that fining upward in the members of this formation. You see the coarser grains at the bottom, the finer grains at the top. So the coarser grains are the grains that were near the shoreline, and then as the water rose, the finer grains were deposited on top of the coarser grains. And remember, this is called an on-lap sequences. The water is lapping onto the coastline. How do we get transgressions? Well, anytime you have water rising, you're going to have a transgression. And how does that happen? Well, one of the ways is melting of polar ice caps. Another thing is displacement of ocean water by undersea volcanism. And finally, you can have local sinking or subsidence of the land in coastal areas. If the water goes up, it's got to come back down. This sea level drop is called a regression, and a regression produces a coarsening upward sequence of facies. So we'll have shallower water facies overlying deep water facies, and of course this is called an OFFLAP sequence. And in this picture right here, we see sedimentation during regression. How do we get this regression? So if we have a buildup of ice in polar ice caps, like with snowball Earth, you can also have the formations of glaciers on land. And finally, if you have localized uplift due to seismic activity, you can get a rise in the coastal areas, which will seem like there is a lowering of sea level. So it's a localized lowering of sea level. In all those instances, you'll get this OFFLAP sequence where the shallower water deposits are going to be deposited over the deeper water deposits. And this is called a sea regression. When we talk about facies, we have to talk about Walther's law. Walther's law is named after Johannes Walther, a German rock star. He was a German geoscientist who developed some important principles of stratigraphy in the late 1800s. One of these principles became known as his law. Now, this law states that sedimentary environments that started out side by side will end up overlapping one another over time due to transgression and regression. You'll know if there is a transgression or regression because the vertical sequence of facies mirrors the original lateral or horizontal distribution of those same sedimentary environments. And you can see this in figure 5-36 below. In one of the labs we did, we looked at correlation. So this is just a review of the correlation we talked about when we did that lab. Now remember, there's lots of different types of correlation. One of them is matching up rock units. Another one, and that's lithostratigraphic correlation, and another one is matching up rock units based on the fossils they contained, and this is called biostratigraphic correlation. And finally, there's matching up rock units on the basis of age equivalency, as determined by radioactive dating method or fossils, and that's called chronostratigraphic correlation. All of these rock units we've been talking about, we talk about them as being perfectly layered one on top of the other with no breaks in these rocks. The time is just constant. Well, the time may be constant, but remember, through time, rock units can be weathered and eroded. So a unit that is on top of another unit, that unit on top may be significantly younger than the unit below because the unit below was weathered and eroded. The place where the two rock units touch each other is called a contact, and those contacts can be conformable or unconformable. Conformable contacts between beds may be either abrupt or gradational. Abrupt contacts are bedding planes resulting from a sudden minor change in the depositional conditions. Another type of conformable contact is gradational, where the contact represents a more gradual change in depositional environments. In one of our labs, we talked about unconformable contacts, also known as unconformities. And this represents a gap in the geologic record because there was either erosion or there was a period of non-deposition. This unconformity can represent a very long period of time, like millions of years, or even hundreds of millions of years. Here are the different types of unconformities we've seen: an angular unconformity at the top, a nonconformity in the middle, and a disconformity at the bottom. Remember that an angular unconformity is where the strata that is below the unconformity meets the strata at the top at an angle. A nonconformity is where the strata at the top meets the layers of rock at the bottom, but where they meet that contact, the rocks at the bottom are either igneous or metamorphic, and on top of the contact, the rocks are sedimentary rocks. So that's called a nonconformity. And then on the bottom, we have our regular everyday disconformity, where there's sedimentary rocks on top of the contact and sedimentary rocks on the bottom of the contact. But what we see is that there was an erosional event or a period of non-deposition that causes a huge gap in time. The other types of unconformities also have a gap in time. It's just the disconformity can be really hard to see when you're out in the field because we have sedimentary rock overlain by sedimentary rock. There's various ways in which the distribution of these rocks, these formations, can be depicted. They can be depicted in geologic columns. Here are some geologic columns, and we can see the rocks in cross-sectional views. We saw this in one of the labs that we did. You're able to use these geologic columns in order to correlate rocks from one region to another. As we can see in this figure over here, these columns are taken from locations 1, 2, 3, and 4. And since the units are very thick and they are deposited over miles, we know that these are formations, and these formations, like the Hasmark formation, can be correlated from one region to the other. Notice how in other, there's the Park Shale right here on the right-hand side, but notice how it peters out. It's still a formation because it goes over a long period. It's deposited over a long distance, right? But it does peter out, of course. So when I look at this column right here, I notice that the Park Shale peters out, right? This Park Shale is shale and siltstone, and shale and siltstone represents an environment that's a low energy environment. So I know that in the past, this low energy environment was in the locality of 2, 3, and 4, but not in the locality of 1. So it gives me an idea of what this area looked like. There was more of a shallow sea in areas 2, 3, and 4, but by the time we got to 1, it was no longer a shallow sea. Remember that because we're missing the Park Shale here, it could be that there was a period of non-deposition, right? That there wasn't a low energy environment where the shales could be deposited, or those shales were weathered and eroded. That's a possibility. By the way, I also wanted to mention what a beautiful figure this is. Whenever I would do a figure like this is exactly how I would want to do it, right? We have the locality of where the cross sections are. We see the types of rocks that there are. And then we have this right here showing the thickness, right? So it's got all the information you need. Also, notice this red line right here. It shows the occurrence of a trilobite. So now we're looking at biostratigraphic units and lithostratigraphic units together. If you've taken a structural geology class, stuff like this looks really, really familiar. So this red line right here represents where the cross section was taken. And here's the cross section itself. It shows the lateral continuity of these formations. The tops and bottoms of the rock units are plotted by elevation. You can see elevation on the y-axis over here, and the folds and the faults are depicted clearly. It takes a lot of practice to get these right. Another way that geologists show the lateral continuity of units is by looking at geologic maps or creating geologic maps. And they show the distribution of various layers and types of rocks in an area. There's all sorts of symbols that go with these geologic maps that you learn in a structural geology class. There's some basic symbols here like the strike and dip of the rock, the formation names. Different colors are going to represent different formations or different rock types. But this is a typical geologic map. Paleogeographic maps are really, really useful. As you can see, this image on the right here represents the Midwest, right? We can see Ohio right there in the center. It's shaped like a heart. So when I lived there, they used to call it the heart of it all. Okay, that's fine. I loved living in Ohio, but I'm not sure whether it was the heart of it all. Anyway, so this is a paleogeographic map, and it's an interpretive map which depicts the geography of an area at some time in the past, showing where there was an island, where there was a delta, based on the evidence we see in the rock record. Notice how Ohio had a shallow tropical sea at this time. This is, of course, the Mississippian period. This Mississippian period in the Midwest has a lot of limestones, and that's what we get from a shallow tropical sea. So we find a lot of limestones and great tropical fossils, right? During this time, we see a lot of crinoids and corals, and that gives us more evidence that there is a shallow tropical sea. Now, with this island here, we probably see some beach facies on here, and in the prograding deltas we probably have a lot of deltaic sediments. And how do we know that there was a delta there? And we look at deltaic sediments of the present and apply it to the past. Again, the principle of uniformitarianism. Here's something called an ISOPACH map. This ISOPACH map shows the Midwest and the East, and it shows the Ordovician Formation in Pennsylvania and the adjoining states there. And the ISOPACH map shows the thickness of formations or other units in that area. So here's that word facies again, and this is a lithofacies map showing the distribution of these facies, these lithofacies, oh my goodness, lithofacies that existed at a given time over an area. So we can see the sandstone, we see the source area. So this is the terrigenous source area for the sandstone. So this sandstone right here probably represented a near shore environment, the sandstone, so a continental environment. So these are the sandstones. And then as you move out, as you're moving west in this case, we see a shaly sandstone representing deeper waters. And then we have a limey shale representing even deeper waters. And then out here we have the carbonates. So this represents a shelf environment where we have the shaly sandstones, we have the carbonates. Remember, carbonates need to be deposited in warmer waters. So look at all of this information we gain from this lithofacies map. So those are all the ways that we can depict the past in map or cross-section form. Wow, we really went through a lot in that last little video there. Remember, we saw lithostratigraphic units, facies, transgressions, regressions, Walther's law, and how we depict all this geology on maps and cross-sections. But that's the end of chapter 5. So the next thing that I'll go over is some tectonics, but that is the absolute end of chapter 5. I know this one was a long video, but I hope you gained a lot from it, and this will be a great way to study all the things you need to know about the sedimentary archives.